Welcome back, everybody, and we will continue on this exciting session looking at what our PhD students are doing. So I'll pass back to Wei, our HDR coordinator. Thank you.
Thanks, Alison. And hi, folks. This is Wei Xiang speaking from Melbourne. I'm the HDR coordinator as well as the Cisco chair of AI and IoT at La Trobe University. We just finished the third session one for the PhD presentation. That was very well received. We got lots of interesting questions. And unfortunately, we slightly go over time. So yeah, but that's a good thing. Yeah. So in the second part of the PhD presentation, we have four more presenters to talk about various topics in relating to the priority areas of SmartSat CRC. To save time, I will encourage you, all the attendees, type your questions in the live Q&A panel as the presentation goes, so we can save some time. Now, without further ado, we're gonna so our first speaker for the second session is Asam Wakas from University of South Australia. And his talk is distributed beamforming for satellite applications. So Asam is currently doing his PhD at the University of South. And before that, he has completed his master in communication engineering from Technical University of Munich in Germany in 2018. So he did a bachelor's degree in electrical engineering from University of Engineering and Technology, Lahore, Pakistan in 2012. And he has 5 years and plus years of working experience in the design of ground station for satellite communication, system design of TTC and a station for LEO satellite, design and development of COTP terminals, and D&D of RF filters and system design for different WASAT applications. And furthermore, he has also worked in in areas relating to electronic circuits, FPGA, MATLAB, and test automation for radio frequency measurements and digital circuit design while working at University of South Australia. Over to you, Asam.
Welcome to the presentation. My name is Ahsan Wakas and I am pursuing my PhD at the University of South Australia. My PhD project is on distributed beamforming for satellite applications, and I got funding from SmartSat CRC for my PhD project last year. So let's start with the presentation. Recently, the consumer market for internet and satellite communication based services is increasing day by day. So the high speed and high throughput low Earth orbit satellites are the future solution to address these demands. For example, SpaceX and OneWeb are launching thousands of satellites to provide internet services, and similarly Myriota and Fleet Space etc. are launching nano satellites for the Internet of Things services for the users and the consumers. So with mentioned advantages of LEO satellite communication, there are some challenges as well, which we will discuss now. The first challenge to communicate with the low Earth orbit satellite is related to the signal transmitted by LEO satellite. The received signal from the satellite has frequency, phase, and time offset. The Doppler offset added to signal depends upon the signal frequency, satellite, and ground terminal relative speed. This frequency, phase, and time offsets needs to be compensated at the ground station or receiver to decode the data successfully. Another challenge is that LEO satellite communication requires a tracking antenna at receiving or a ground station. Now we will discuss two methods to track the LEO satellites. The first method is mechatronic approach, where we mechanically move antenna at the ground to track LEO satellite as shown in figure on the left side of this slide. However, tracking antenna has a couple of issues, like it is usually bigger in size and that's why it's quite costly, and its transportability is an issue, and it requires um, continuous or more maintenance because of mechanical wear and tear and rapid switching, and it can cause the single point failure. If antenna is mechanically broken, then we will not be able to track and communicate with the satellite. And if we want to track multiple satellites, then we need multiple or more antennas. In second approach, we have fully electronic approaches where we do not move antenna mechanically, rather electronically we control the beam of antenna. These techniques include phased array antenna technique. As depicted in the figure, we have multiple fixed antennas which are located at one place, and we apply a different phase offsets to each antenna element to steer the beam in certain direction. And this second method of electronic approach is the distributed antenna technique. In this technique, we have multiple fixed antennas terminal which collaboratively receive or transmit the signal from or to the satellite. If distributed antennas collaboratively receive the signal from satellite, that is called the distributed receive beamforming. And if these nodes or these distributed antennas collaboratively transmit the signal towards satellite, that is called the distributed transmit beamforming. In my PhD thesis, our focus is on distributed receive beamforming. Next, I will explain the distributed receive beamforming. In distributed receive beamforming, we have two main components: nodes and the fusion center. Nodes receive the signal from the satellite and forwards after some processing like time, frequency offset corrections, and downsampling towards the fusion center. Then fusion center combine the observation of all nodes. The fundamental principle of distributed receiver beamforming is that we combine signals from all the nodes coherently. As signals received at each node experience different time, phase, and frequency offsets, we need to estimate and correct these offsets before combining the signals of different nodes. As shown in figure, when we combine two sinusoids without any offset, we get 2 times increase in signal to noise ratio. Distributed receiver has many advantages, like it enhances the signal to noise ratio of the received signal, and it removes the single point failure which results in increased reliability of our receiver, and we can add more and more nodes in a distributed receiver without disturbing our whole system. So scalability is quite easy, and by increasing the array size we can get the more directed beams, and so this results in a greater spatial resolution. Now I will explain our system assumptions. We consider the case where receive nodes can communicate with a central node like fusion center. Any node could take the role of the fusion center, but we will treat it as a separate node without any directly received signal as shown here. We further assume that the communication links between the nodes and the fusion center permit bidirectional data exchange but do not allow clock synchronization. These links can be wired or wireless network links based on the IP protocol. This constraint is different from recently reported work in the literature that considers that dedicated links for transfer of reference signals to achieve the synchronization between or among nodes. We further consider a situation where we have a capacity limitation on the links between nodes and the fusion center. So we aim to reduce the amount of data exchange between the node and the fusion center. For example, by downsampling the received signals at the nodes to simber rate and then forward it to the fusion center. Now I will discuss about work done until now. First of all, we explored that we want to enhance the frequency estimation at one node by the collaboration of other nodes and the fusion center. And first of all, we explored that which information other nodes and the fusion center can send to a node with smaller signal to noise ratio to improve its frequency estimation accuracy. We propose different methods which improves a node's capability with the exchange of minimum symbols from other nodes or from the fusion center. So we have written one journal paper which is right now under review at IET Communication. In the second problem, we are dealing with the joint iterative decoding and Doppler rate estimation. In the second problem, we consider that Fusion Center has access to downsample data of each receive node, and we proposed a message passing based algorithm. We used particle filtering technique where the intractable messages comes in. So in this problem, we have written one conference paper which is being accepted in IEEE LatinCom, and one journal paper is right now in progress. In next problem, we are interested to put the capacity constraint on links between nodes and the fusion center, and we will work on beamforming algorithms when we forward hard decisions and or soft decisions under frequency offset from each node towards the fusion center. There are few interesting applications of the distributed receivers which we can discuss now. Consider a group of soldiers are in the battlefield and they cannot carry a big tracking antenna. However, each of soldiers has a small devices like radio. By the collaboration of these devices, soldiers can receive commands or data from the remote headquarters. And this, as a second example, groups of wireless sensor nodes can receive updates over a satellite downlink from a remote location or a remote headquarter or remote user. And the next application is search and rescue, which is depicted in this figure here. A distress signal is sent from a transmitter from a remote location where any emergency has happened. This signal is relayed from multiple different satellites towards a distributed receiver. The distributed receiver forms multiple beams, one to each satellite, and tries to find the transmitter location by using frequency difference of arrival and time difference of arrival of these signals. So there are many interesting applications of distributed receiver we can think of. This concludes my presentation. Thank you for listening me. If you have any questions, I'm happy to answer them. Thank you.
Thank you very much, Hassan, for your interesting presentation. Yeah, I would say distributed beamforming or beamforming as a whole, or sometimes called pre-coding, is one of the most classical research problems in communication engineering fields. And my question for you is that there's some recent development. I'm not sure you have noticed. One thing is moving from traditional signal processing theory-based beamforming to deep learning-based beamforming. That's one direction. And second direction, particularly in the area you're very applied to your area, distributed beamforming, is the advance of so-called reconfigurable intelligence surface called RIS, because RIS can dramatically increase the so-called degree of freedom of the beamforming, because it has multiple, a large number of smaller surfaces which it can control. So have you thought about combining some of the latest developments in the beamforming into your research project?
We might think on the IRIS, the intelligent refracting surfaces, because major focus up till now on my PhD thesis on the estimation side of, estimation of the parameters, frequency, and the phases, how the distributed antennas should be combining their signals. So my major focus was on the, when we have the downsample data, then the estimation of each of the node decreases. So how we can enhance their capability to estimate better. So in short, my whole focus was on the estimation side up till now. Yes, we can include the further improvement or the advancements like IRS in to enhance the capability of the beamforming in future as well. That's certainly a chance and the future horizon we have.
Great. You already considering risk because it's been very hot in the beamforming space. The other question is, because once you're starting to think about risk, and I think the optimization problem becomes very complex.
Yes, right.
Because of the number of the surfaces we're dealing with. So there's a lot of work you're talking already starting to shifting away from the traditional interference, minimizing interference-based theory into the deep learning, using a data-driven approach.
Yes.
I think, what's your opinion? Do you think that's a master and, we have to use a data-driven approach, or do you think, we can still using conventional interference by minimizing interference? What's your opinion on this?
So up till now, it's the data-driven one. So, but we can increase the capability of our system, obviously, by considering both of the concepts and ideas which you are talking about right now.
Yeah. We have one more question from the audience. Yeah. So does this approach allow energy recovery in multiple party channel or multiple channel? Yeah.
Sorry, energy means?
So energy recovery. So in a multiple channel scenario, so your approach will enhance the energy or recover more energy in this scenario. That's what this question is asking.
So energy means that we have the access to the multiple signals from, one source, let's say, and then we combine the signal strength from all the sources, and then we can ultimately increasing the signal to noise ratio. You can say that. So in one way, we can say that the energy of the our received signal is enhanced in that sense. Yeah.
Yeah. Great. Yeah, I agree with you. Yeah. I think the essence of the beamforming is you have advantage of receiving, the same, providing synchronization is guaranteed. You can
yes, exactly.
channel from multiple. The signal transmitted through the multiple channels.
Yes, right.
Yeah, excellent. Yeah, so thank you very much once again for your interesting presentation. Yeah, I think beamforming is
Thank you.
Very interesting in terms of advanced communication for the satellite system.
Thank you so much.
So moving on to our next speaker, Benjamin Dix Matthews. He's going to talk about his presentations about coherent free space optical communication. Unfortunately, Benjamin is not available to answer question, in person. He has asked us, anyone interested in his project. He's got his email written down in the slides at the beginning. So please feel free to get into touch if you have any question for Benjamin. Yeah, so the bio for Benjamin is that he's currently a PhD candidate at University of Western Australia. And he's working on a stabilization of free space optical links for metrology, geodesy, and comms. And he has previously completed a master in electronic engineering and has lots of experience in the technical progress of designing, prototyping, and testing electronic and electrical and optical systems. So Ben's research is largely focused on leveraging phase technology developed at University of Western Australia and applying that to ultra-stable optical signal transmission through the atmosphere for use in high-speed comms, geoscience, and fundamental physics. And his work has led to international collaboration with both private and public organizations around the world. His first also papers including research into cutting-edge technology for orbitography, optical clock comparisons, and high-speed optical communication. So over to Ben. Yeah, so his presentation has been pre-recorded. So let's have a listen. Thank you.
Hi all, my name is Benjamin Dix-Matthews, and I'm currently approaching the end of my PhD, which has been supported by a number of different funding bodies that are shown here, including the SmartSat CRC. Also listed here are my supervisors at the University of Western Australia, as well as my project partners for the SmartSat portion of my work. So, the aim of my project has been to develop systems capable of coherent optical transmission through atmospheric turbulence. So I'm going to start off by unpacking a few of these terms. So by coherent, I mean we're using a continuous beam as opposed to a pulsed laser. By optical, I mean that we're using laser beams as opposed to radio frequency or microwave frequency technology. And through atmospheric turbulence, I mean that we are transmitting wirelessly through the moving turbulent atmosphere. So what is atmospheric turbulence? Within the atmosphere, there are constantly fluctuating refractive indexes. And as our optical beam propagates through these, it alters the propagation of that signal. There's a 0th order piston mode effect, and that causes time of flight variations, which in turn induces phase noise onto our transmitted signal. And that in turn degrades the phase and frequency stability of that signal. There's also first order beam wandering effects, and that leads to spatial variations in the centroid of the beam. And that in turn causes intensity fluctuations as we attempt to receive that optical signal. So during my PhD, I have worked on developing systems capable of suppressing these effects. So to suppress the 0th order piston mode effect, we use a phase locking system essentially. So we transmit our laser signal over our free space link, and then at the far end, we reflect a portion of the signal back over the link. So during the forward pass, we experience a certain amount of atmospheric phase noise, and during the reverse pass, we experience the same atmospheric phase noise due to the reciprocity of the atmosphere. We then measure how that phase fluctuation has changed the phase of our beam, and then we pre-compensate for whatever phase change the atmosphere is imparting. And that means we cancel out this phase change, and we maintain the phase stability and frequency stability of our transmitted signal at the receiver. There's also, to correct for first order beam wandering effects, we use a quadrant photodetector to measure the position of the incoming signal. So we receive our optical beam, we bounce it off this mirror through a Galilean beam expander, and then use a beam splitter to send a portion of it to this quadrant photodetector, which is sensitive to lateral deviations in that incoming beam. We then use that measurement of lateral deviation to control this fast steering mirror, which then cancels out whatever those movements are and means that we suppress the beam wander and maintain lock on the target, the far end, reducing scintillation effects. So this is a video of what that actually looks like. So when with tip tilt off on the left, we see that the beam is moving around all over the place. And when we turn on that stabilization system, we can see that we're nice locked on and it's not moving around too much. So with those armed with that technology, my PhD has involved demonstrating it over a number of different link architectures. So the first and easiest architecture is a folded link. So that involves transmitting the optical beam to a retroreflector. So there are also some applications, actual science applications that use this type of architecture. And the application that I focused on for my PhD was Doppler orbitography. So that involves transmitting our optical beam through the atmosphere and reflecting it off a satellite. That satellite is moving, which will then impart a Doppler shift on that optical signal. The return signal, we can then measure how that frequency has changed and perform a measurement of what the actual speed of that satellite is. I demonstrated the key results of my experiment were that you should be able to achieve uncertainties of around 1.1 nanometers per second when averaged over 60 seconds. And that represents a 4 order of magnitude improvement over current state-of-the-art RF and microwave techniques, which is impressive. However, it should be noted that these demonstrations were over 1.1 kilometer terrestrial links, as opposed to actual ground to space links. So there's a few challenges that need to be overcome so that this technology can actually be used for Doppler orbitography. A step up in terms of architecture complexity is to perform full point-to-point optical transmissions. The application that I focused on for my PhD was Chronometric Geodesy. So Chronometric Geodesy involves measuring time shifts between optical atomic clocks by performing clock comparisons. So the way optical clocks are currently so accurate that a shift up or down by 1 centimeter imparts a gravitational redshift that is actually measurable. So if you are capable of performing clock comparisons at levels limited by the actual stability of the clocks, it means you can directly measure gravitational redshifts on the order of 1 centimeter, which is pretty impressive and provides an entirely new avenue for performing geodesy measurements or measurements of the Earth's gravitational field. Some key results for this demonstration was I built a robust and transportable system. So I developed a system at the University of Western Australia and shipped it over to Toulouse in France for a collaboration with the French Space Agency. And we demonstrated the most stable, coherent laser transfer that's ever been achieved over a point-to-point link. So in this plot on the right, you can see that we have our fractional frequency uncertainty. So this is the uncertainty in our received signal, optical signal, and that averages down over time. You can see after around about 0.1, about 100th of a second, we surpass the stability of the best atomic clocks in the world. We then average down continuously to a level where we're actually surpassing those clocks by over an order of magnitude after about 10 seconds of integration. So that means that we can really do clock limited comparisons between 2 optical clocks, which is a prerequisite for chronometric geodesy. The third demonstration is for stabilizing a wideband signal. So up till now, all of the experiments have involved metrology signals, so where the goal is just to have a high degree of measurement accuracy or precision. For high-speed data transfer, you need to actually modulate data onto that optical signal, which means you then spread optical power into the wideband. So you want to make sure that your system is capable of stabilizing not just a narrow line, but a wide area of the spectrum. So the key results for the system that I built was that for phase noise at a 10 hertz offset, you get a 1,000 time reduction in noise over a full 7.2 terahertz range, which is large. That is the entire C-band. It encompasses the entire optical C-band, which is pretty impressive. And this means that the types of stabilization systems that I've been demonstrating so far could be used to actually stabilize a communication signal without ruining the stability of that communication signal, which is an important step forward, an important thing to know. So in summary, during my PhD, I have developed technology for the stable transfer of laser signals through atmospheric turbulence, and I've demonstrated their value in a number of different applications. The next steps for me and my group is to build Australia's first optical ground station. So that is shown here, and that will be on the roof of the University of Western Australia's physics building. And when that is commissioned, it's already commissioned. When it is finished with testing, we will then use it to attempt a true ground to satellite transmission, which will be exciting and I expect challenging. But yes, very exciting things in the future. So I'll leave you with that. I'm not able to do a answer question session for this conference. So I've provided my email there at the bottom, and please feel free to send me an email if you have any questions about any of the content that I've gone through today. So thank you again, and thanks for your time.
Benjamin, yeah, so I found his presentation interesting, and I hope you enjoyed his presentation as much as I did. Unfortunately, yeah, Ben sending his apologies. He's not available to answer question, attend the live Q&A session. So he left his email address in the last slides. So feel free to get into touch with him if you do have any questions for him. So now we'll move on to our next speaker, Thomas Graham at Swinburne University. The topic of his presentation is responsible AI in space. A little bio for Thomas. So he completed his Bachelor of Science at the University of Melbourne before becoming Juris Doctor in Space Law, and also at the same university. Yeah, and utilizing his education in both physics and law brings a unique perspective into legal regulatory issue relating to AI in space. So he has a passion for space law, intellectual property law, and artificial intelligence. So let's listen to what he has to share with us.
Hello, my name is Thomas Graham, and I am a PhD student at Swinburne University of Technology. My project is on responsible AI in space. I'd like to begin by acknowledging the traditional custodians of the land on which I'm recording this presentation, the Boonwurrung people of the Kulin Nation, and pay my respects to their elders past, present, and emerging. I'd also like to give a disclaimer that I'm very early in my project, and so I don't have any results yet, and a lot of the scope and methodology for the project is still being determined. Because of this presentation will focus on my plans for the project going forward, the areas I want to explore and the topics that I believe we'll focus on. Much of this is still subject to change potentially, given how early I am in this project. This project is actually based in law rather than computer science, even though it is about AI and space. However, due to the nature of AI and machine learning systems, as well as space technologies, and the intersections of all of those fields, it will necessarily take on a multidisciplinary flavor. I want the project to take a pragmatic approach, generating meaningful and actionable guidance for industry to help facilitate capability building in the Australian space and AI industries going forward. To that end, the aims of this project are, as on the slide, to investigate current regulatory approaches to the AI industry, to determine what guidance Australian industry needs regarding AI being developed for space applications, and to produce and validate a regulatory framework tailored to the Australian space industry's AI activities. The exact form that this framework might take is obviously yet to be determined. It could constitute hard law, being sort of laws of parliament, other binding regulations, or it might be soft law, being guidelines, codes of ethics, and other non-binding guidance. The exact form that is recommended will obviously depend on a number of factors, such as the effectiveness, the compatibility with other legal frameworks, government and industry compliance and willingness to support such a framework being put in place and to comply with the final framework, and likely many other factors. Looking at my past research, I focused on the regulation of ethical AI systems, ensuring they're safe for consumer use and that they will not be used or cause unintended harm or infringement of personal rights. I've examined all sorts of issues with what causes these AI and ML systems to go wrong, such as negative feedback loops, which are often caused by bad or dirty data, as it's sometimes called, as well as opaque black box algorithms that operate beyond the scope of human oversight and even at times beyond human intelligibility. As a part of this, I looked into the qualities needed to be imbued into these algorithms and systems to make them operate in an ethical manner. These include accuracy of operations, transparency of data acquisition and processing systems, accountability for the owners and operators of the systems, and contestability of the system's final decisions for those who have their interests or rights affected by the decisions of such systems. I've also investigated the controls needed to ensure ethical AI can be achieved. These include training ML systems using only clean or curated data, having a development culture that understands the potential impacts and consequences of their work, having reporting procedures to ensure adverse outcomes can be logged, investigated, and rectified, and having effective oversight bodies to maintain external industry-wide standards and, of course, regulation at the legislative level. This research bridges into the current project quite well, as many of the principles of ethical AI systems can be transposed to responsible AI. And so the question becomes, how can these principles about ethical and responsible AI, without getting into the semantics about the differences between those two, be transferred into the space domain? Now, when you're thinking about regulating the development and deployment of AI in space, you have to ask, what makes space special? What is it about the physical nature or political nature of operating in outer space, or the particular use cases where AI is deployed in space, that merits special consideration and reconsideration of the generally agreed upon principles for responsible AI development and operation? Firstly, we can think about latency. Often when it comes to AI systems, a popular control put in place is to require that there are human in the loop or human on the loop type setups, meaning that there will be still some level of human operation of the system, whether that's that humans need to give final approval or merely that humans can interject and override the algorithms in order to manually adjust the system. However, the vast distances associated with space travel and communication between objects in space mean that if, for example, there were a situation where satellites were in orbit around Mars and were being controlled from Earth, and they needed to maneuver to avoid colliding with each other, for the sake of safety and accuracy in any maneuvering systems, it would be appropriate to accept that AI must have near total autonomy in controlling the satellite, as human control signals coming from Earth would be delayed by minutes, making them potentially inaccurate or untimely, leading to an accident. Given outer space is beyond national jurisdiction, the UN space treaties and the principles espoused within them are also important in determining the governing framework, which will dictate how organizations can lawfully carry out their activities in space. A particular example of this is related to liability in the case of fault. The Liability Convention, which is one of the UN space conventions, currently has a two-pronged system of liability, with the exact type of liability being either fault-based liability for damage occurring in space, or absolute liability for damage occurring on Earth. This system is confusing, and without adding AI to the mix, it's confusing, but when you add AI, it's even worse. Issues of fault can become further muddied given the often indirect and subtle ways in which AI systems can be influenced to come to different outcomes and decisions. As such, this represents an area where international law could have a substantive effect on the operation of AI systems in space in a way that needs to be further investigated and understood. Finally, for this slide, we have more traditional commercial concerns of intellectual property, trade secrets, and confidentiality. Space technology and AI technology are both at the forefront of global technological innovation, and as such, these systems and the knowledge relating to them are incredibly valuable and often protected. Because of this, and the protections that certain legal regimes such as intellectual property and trade secrets provide, you have to ask, how can these systems be examined and certified as being trustworthy without breaching said legal obligations and protections, or perhaps even contractual clauses? On this slide, I've listed a few examples of how AI and ML systems can be deployed in or adjacent to space. Some of these are even happening now. This is obviously a short list, and there are many more examples popping up all the time. The current plan is to focus on 3 use cases in bolded font: the Earth observation and imaging systems, space traffic management, and space weapons systems, as they are examples which are both broad and they are of economic and political significance, making understanding them key to being able to foster industry growth going forward. As I said before, I'm still early in my PhD project, and so I still have a lot of questions that need answering. I have a few of them listed here. So the first is, what are the use cases of AI in space? I had some on my previous slide, but I'll need to find more and know more about them all. Beyond this, it will be important to distinguish between AI in space in situ and AI situated on Earth, being applied to data gathered in space. This is because the physical location of the AI system may cause international law to be enlivened or not, or the domestic legislation of a particular country that it is located in to be enlivened or not. There is also the potential for each of these use cases to affect the rights or interests or opportunities of particular people or organizations. This will affect how they need to be regulated. We must also consider how these AI systems can be regulated to ensure they're more responsible. In some ways, responsible is analogous to ethical, as I briefly touched on before. And without getting into semantics, the question can be, how can we first determine which principles of ethical or responsible AI systems can be directly transposed into the space domain and which ones cannot? And then beyond that, which ones must be modified in some way to make them appropriate for the space domain? Then there's the question of what guidance does the Australian space industry want or need to optimize their projects going forward? Would the industry prefer a soft touch approach without binding regulations, more focused on voluntary guidelines and codes of practice, or would it prefer a traditional legal approach, mandating standards across the industry to feel assured and be confident that all AI systems utilized in the industry are developed to the highest standards and operate only under careful supervision? Finally, for this slide, we must ask, what protections do consumers need to ensure that these systems are ethical, trustworthy, and safe? In this context, consumers are more likely to be institutional or organizational consumers, given the applications of AI to space technologies. Regardless, concepts of ethics, trust, and safety need to be considered because these consumers nevertheless want the systems they use or are connected to be safe and secure, and to avoid costly errors or data or privacy breaches that could affect not only their legal liability, but also their organizational reputation, potentially even losing revenue in other parts of their businesses. As such, in order to ensure an industry where consumers are comfortable using AI systems and adopting them widely, the trustworthiness of these systems must be ensured. This brings me to the end of my presentation. As I said, I'm still early in my project, and so it was quite light on details, and I apologize for that. However, I do hope you found it interesting. If you have any questions, comments, or advice, I'd love to hear them. Please feel free to reach out to me at the email address on the slide. Thank you.
Thanks, Thomas, for the interesting presentation. I think your presentation is unique in the sense, most all of the others are looking at where's the issue from the technology perspectives, but yours is looking from a unique, law and regulatory perspectives, and I find it quite interesting. So, a question here from you. I confess I'm not an expert. I've got nothing to do with law, but I think slightly related, not exactly the same topic. Of course, it's called in the AI space. It's called explainable AI. So this is traditional AI is black box. It just tell you what to do. It doesn't tell you a reason. Yeah, but this so-called explainable AI is going to turn the black box into white box, so it can provide information and tells the decision makers, policy makers, to system as decision was made in the first place. So, do you think that this new direction of AI is going to help you your research in terms of response to AI for space?
Yeah, well, it's interesting. Obviously, ideally, you want those white box systems, explainable systems, as you described them, and that's sort of the push that we're having. Especially led by the European Union with their new laws and legislation coming through. But when you think about the space domain, the primary, and this is something I'm going to have to investigate further, but the primary consideration is almost certainly going to be the accuracy of the systems. You want them to be perfect and not make a mistake, because a single mistake could result in the destruction of very, very valuable equipment and the creation of space junk and stuff like that. And so to the extent that less explainable systems are more accurate, that may be a trade-off that has to be accepted when it comes to deploying AI in the space domain, compared to, I'll say, just terrestrial AI that's applied to the sort of consumer transactions and things like that.
Great. Yeah, Thomas, we have one more question from the audience for you. So are there positive or successful examples in the regulation policy making around ethical AI in non-space sectors that could serve as like encouragement that similar success can be achieved in space?
Yeah, so largely around the world, I mean, there's not much regulation of AI in general, certainly not in the space domain, which is why this is an interesting topic to be working on for me. But the EU right now is working on a risk-based framework of legislation and regulation. So the higher the risk of a particular use case of AI, the more strictly they'll regulate it and the more controls they'll put on it. Now, that's actually not been completely passed yet. I don't think it's even finished being drafted, but it is well and truly on its way. And I think it's fair to say it's sort of the world-leading example of AI regulation. And when I think about what sort of frameworks I might be designing for the space domain when it comes to AI, that is certainly sort of the prime example I would be looking at of whether I could transfer a lot of the elements of that risk-based model into the space domain directly or with some modification.
Yeah. And Thomas, I can tell you, we just received a comment from our CIO, Carl, and he liked your presentation, and he thinks it's certainly a very interesting and important direction to explore. So congratulations again for your presentation, and looking forward to hearing more exciting results out of your research. Thank you.
Thank you.
Our final, last presenter, obviously not the least, is from Sabrina Slimani from University of Adelaide. So she's going to talking about something very exciting about quantum technology. And we all know, quantum technology is said to be revolutionize the way we live our life in the next decades, and is going to fundamentally change everything to do with digital technology. So her presentation is about using quantum entanglement to remotely synchronize clocks. So Sabrina is currently undertaking her PhD with the Institute for Photonics and Advanced Sensing at University of Adelaide. And Sabrina was conferred a Bachelor of Science in the major of Experimental and Theoretical Physics, and subsequently honors degree in Bachelor of Science in 2020. So at University of Adelaide. So she was a fresh graduate last year and went straight into her PhD. And her current research involves using quantum mechanics to develop a secure protocol to synchronize the clocks in the space. Over to you, Sabrina.
Hello, everyone. Thank you for attending the SmartSat conference. My name is Sabrina Slimani. I'm a PhD candidate at the University of Adelaide, and my PhD project is about using quantum entanglement to remotely synchronize clocks. As part of my presentation, I'd like to acknowledge and thank for their contributions my supervisors, Dr. James Quach, Dr. Ben Sparks, and Professor Andre Luton. I'd also like to thank Dr. Fred Baines and Nicole Ewan for the work that we're doing together. And I would also like to acknowledge the funding provided by Defence Innovation Partnership for this project. Allow me to begin my presentation by asking you to consider what clock synchronization is and why we require clocks to be synchronized. When we synchronize clocks, we require the clocks to show the same time and to tick at the same rate. Clock synchronization is required for accurate time and data transfer across terrestrial to satellite links, such as in global navigation satellite systems, and clock synchronization is also required in telecommunications. Without accurate clock synchronization, data loss can occur, which has ramifications for the proper functioning of electricity grids, finance sectors, and also in health and defense. Time transfer signals are also required to be secure. However, such signals can be spoofed or jammed, resulting in false or no time and location information being provided by the global navigation satellite systems. Two current classical clock synchronization techniques I'd like to share with you are named after Sir Arthur Eddington and Albert Einstein. The Eddington method involves having both clocks in front of you, setting them to the same time, and then sending out one of the clocks to the desired location. Clock time can drift due to environmental factors and clock aging. Therefore, in space-based applications, resynchronization of clocks via the Eddington method can be considered impractical. The second classical technique I'd like to share with you is the Einstein method. In this method, when we have two clocks, the method involves sending a light signal from the first clock and then having this light signal reflect from the second and travel back to the first. The time difference between the two clocks can be calculated by using the time the light signal was sent from and received by the first clock. The Einstein method assumes that the light path between the clocks is the same in both directions, and this is not the case for rotational reference frames. More recently, quantum clock synchronization protocols have been proposed as a means of providing authentically secure time transfer. And while research in this field has been performed over fiber, quantum secure time transfer has yet to be achieved over free space. The goals of my project are to use entangled photons to synchronize two clocks over a free space link. As part of this work, I want to be able to determine how quantum time transfer is affected by loss, background photons, turbulence, and a moving platform. So what is quantum entanglement? Classically, if we think of the computer bit as taking the value of 0 or 1, the quantum version of this is called the quantum bit or qubit. The qubit can take the value of 0 and 1. If we have two qubits that are entangled, then this means that when we make a measurement of one of those qubits, the result of this measurement allows us to determine the result of the other qubit without having to measure it. This entanglement was described by Einstein as spooky action at a distance. To illustrate this to you, let's say, for example, that I had two qubits, A and B, that are entangled, and I can represent them by these spinning arrows. Because they are entangled, then after a certain time, if I measure A to be pointing up, then I know that B will be pointing down. And a certain time later, if I measure A to be pointing to the right, then I know B will be pointing to the left without having to measure it. As part of my project, I'll be using the optical setup shown on the left to generate entangled photons. And it is with these photons that I will be aiming to achieve the goal of free space quantum secure time transfer. In the meantime, we've used an off-the-shelf correlated photon source to achieve time transfer over 100 meters. Our correlated photons are generated by a process known as spontaneous parametric down conversion. In this process, we have a 404 nanometer laser shining to a nonlinear crystal to produce photon pairs that are correlated in frequency and time. The idler photons generated from our correlated photon source travel through fiber to our detector. These detections are then recorded by our time tagger. The signal photons generated from our correlated photon source travel through fiber to our transmit rig. The signal photons travel through the optics of our transmit rig, allowing these photons to be propagated a distance of 50 meters to this retro. The signal photons are then reflected back to return the 50 meters to our receive rig. At this point, the signal photons travel through the optics in our receive rig and are coupled into fiber and travel to our detector. The detection of our signal photons is then recorded by our time tagger. We use the information from our time tagger to produce this plot of the correlation counts between our signal and idler photons. The time at which the peak of our correlation counts occurs allows us to determine the time offset between our signal and idler photons. In the setup I showed to you on the left, we have a known delay of 600 nanoseconds, which we've accounted for in our time tagger. And this is why the peak of our correlation counts occurs at 0 nanoseconds. In our setup, we've performed 2 tests. The first is to see the amount of loss this system can accept via the introduction of neutral density filters at this point of our receive rig. The second test is to determine the effective noise photons, which we introduce into our signal photons into this fiber here, just prior to our detector. We fitted a Gaussian function to each of our correlation plots to assist in analysing our results. To analyse our results, we considered the data for which our correlation plots were clearly evident. From here, we considered the peak value of the Gaussian function fitted to our correlation plots, the peak value of our correlation count data, and also the integration of those correlation peaks. We needed to integrate our correlation peaks to take into consideration the total number of correlated photon pairs that we were detecting. The plot on the left shows you how these 3 measures of photon counts differ with noise level photons. And what we can see is that these photon counts remain relatively constant. From our results, we have shown that we can still detect a correlation peak if our noise photon level is 500 times higher than our signal photon level. The plot on the right shows you how these same measures of photon counts declines exponentially with total loss introduced into our system. What we have determined is that the total loss accepted by our system is 37 decibels. This total loss takes into consideration the loss we introduced via our neutral density filters, but also the loss that was present in our system due to the optics. The next step in this project is to use the entangled photons to achieve quantum secure time transfer, first of all in our lab. In addition to measuring the total loss accepted and background noise level accepted by this system, I'd like to determine the effect of turbulence and a moving platform on time transfer. The ultimate goal is to then use this setup to synchronize 2 clocks and achieve quantum secure time transfer via satellite. Thank you for listening.
It's a very interesting presentation. I don't think any one of us can overemphasize the importance of clock synchronization, because without it, our everyday life will be mess. You know, all our digital technology wouldn't work. Our financial industry will be totally throwing the mess immediately. Yeah, quantum, entanglement, it's quite an interesting topic. So I'm not a expert in quantum. I'll have to confess myself. Yeah. So, but an interesting question arises. What do you think? When you do the experimentation, yeah. So the distance of this your clock synchronization through quantum entanglement, how far the distance you can go up to?
That's a really good question, Wei. There has been previous research done, not quite using entangled photons, but rather using single photons, which is another form of secure time transfer. And this has been done in terms of achieving that time transfer between the satellite and the ground station. One of the limitations of that research was that although they used single level photons, these weren't sort of true signal photons. So it can be sort of debated as to how secure their time transfer is. So with the entangled photons, we're sort of achieving a better level of security in that time transfer, and we're sort of aiming to achieve that over an equivalent distance.
Yeah, we have another question from the audience. Want you to comment on the 500x, the noise versus signal, and the audience thinks it's amazing. So and that's a 37 dB loss limit. Yeah. So do you have any further comments on that?
Yeah, that 500 times noise compared to signal photons was a comparison of the number of noise photons that we could introduce into our system compared to the number of signal photons that we measured in our system. This correlated photon source produces a very low photon rate of correlated photons, and that is why we have a very low number of signal photons. However, that the correlation is still present despite the background being present. And in terms of the 37 decibel loss that we've observed in these preliminary results, what we've observed is that this is the limit at which we can still observe an accurate offset, time offset of our correlation peak.
Thank you. Thank you very much, Sabrina, once again for your interesting presentation. And I think thank you to young researchers, brilliant researchers like you, and proudly supported by SmartSat. Australia is regarded one of the leading country in quantum technology. So we highly appreciate your research, and we're proud that SmartSat is supporting your research, and hopefully to see more exciting outcomes from you. So this concludes our PhD presentation, and thank you everyone for your attendance. And before we finish, I would like to bring your attention to the two poll questions posted early in the session. I'm very pleased to see our academic attendees, 100% of them have indicated strong interest in working with the industry partner in terms of developing industry-driven PhD topics. And they're really willing to spend time with the industry partners. And also likewise, pleased to see the industry attendees and have a very diverse interest in terms what kind of research topics they want, from AI, machine learning to advanced comms and IoT, remote sensing, etc. So I would like to take this opportunity to ask, send a message to our industry attendees. If you would like to have a PhD student topic or student topic you would like to propose, please get into touch with me, and I will be very happy to link you with aspiring academics, core universities. So thank you again for everyone, and now formally concludes the PhD presentation sessions.
Okay, thank you, Wei, and thank you, everyone. I think we're fairly clear that the future of space into the next decade is well underway with the PhD projects we've been looking at. We'll head straight off into our next session now, which is looking at professional development aspects for our PhD candidates. I'll see you in the next session. Thank you, Wei. Thank you, presenters.
Thank you, Alison.